Imagine holding a simple wrench in your hand. It feels cold, solid, and almost ordinary. But what if I told you that this tool has survived forces strong enough to bend steel, temperatures hotter than flowing lava, and manufacturing processes that push metal to its absolute limits? Most people never think about it. But every forge tool begins an incredible journey deep beneath the Earth's surface. Today, we're stepping inside one of the world's most fascinating industries to discover how raw rock transforms into tools trusted by mechanics, builders, and engineers everywhere. Think about this. Every second, thousands of forge hammers, pliers, wrenches, and chisels leave factories around the world. Each one must withstand crushing impacts, twisting forces, and years of abuse without breaking. But here's what nobody tells you. The secret isn't the shape of the tool. The real magic happens deep inside the metal itself, where invisible changes in its structure create incredible strength. And what happens next surprised even experienced engineers. Over the next few minutes, you'll witness giant hydraulic presses delivering thousands of tons of force, furnaces glowing brighter than the sunset, robots working with incredible precision, and skilled craftsmen making split-second decisions that no machine can fully replace. We'll follow every step, from raw iron or pulled from distant mines to the final inspection that decides whether a tool earns its place in your toolbox. By the end, you'll never look at a forge tool the same way again. Every forge tool starts with one essential ingredient: high-quality steel. Much of the world's premium forging steel begins as iron or extracted from enormous open-pit mines in Australia, Brazil, Canada, and Sweden. Some mining trucks carry more than 350 metric tons of rock in a single trip, making an ordinary dump truck look tiny by comparison. Hidden inside that rock lies the metal that will eventually become a tool capable of lasting decades. After blasting and crushing, the ore travels through powerful magnetic separators that remove unwanted rock and increase the iron content to around 65% or higher. From there, enormous freight trains stretching more than 2 kilometers long haul millions of tons of ore to coastal ports. The journey can cover well over 1,000 kilometers before the material even reaches a steel plant. Most people never realize that a simple wrench has already traveled farther than many people ever will. But iron alone isn't enough. Engineers carefully blend carbon, chromium, vanadium, molybdenum, manganese, and sometimes nickel into the molten steel. These tiny additions, often less than 1% each, completely transform the finished tool. One improves hardness, another increases toughness, while another helps the steel resist rust and wear. It's a recipe measured with extraordinary precision, because even a small mistake can weaken the final product. Inside modern steel mills, electric arc furnaces recycle huge amounts of scrap steel alongside fresh raw materials. Temperatures climb above 1,600 degrees Celsius, or nearly 2,900 degrees Fahrenheit, hot enough to melt solid steel into a glowing orange river. The roar is deafening, the heat feels overwhelming, and every movement demands perfect timing. This process not only creates premium steel, but also reduces the need for mining new raw materials, cutting energy use and emissions. The molten steel solidifies into billets, long, thick bars that may weigh several tons each. Every billet undergoes chemical analysis using spectrometers that verify the alloy composition within extremely tight limits. If the chemistry falls outside specification, the entire batch can be rejected before a single tool is made. That's because perfection starts long before the first hammer strike. Next, those heavy billets travel by rail and cargo ship to specialized forging factories across Germany, the United States, Japan, China, India, Italy, and many other manufacturing hubs. Some shipments cross entire oceans before reaching their destination. Imagine the journey, from ancient rock buried underground to refined steel traveling thousands of kilometers across continents, all before becoming something you can hold in one hand. Now the real transformation begins. In the next stage, these ordinary-looking steel bars will enter furnaces hotter than volcanic lava, before gigantic forging presses crush them with thousands of tons of force. The glowing metal will twist, stretch, and flow like soft clay, but instead of becoming weaker, it will grow dramatically stronger. And this is where the science of forging becomes truly extraordinary. The moment the steel billets arrive at the forging line, the countdown begins. Workers and automated feeding systems load each billet into an induction furnace, where powerful electromagnetic coils heat the metal evenly to between 1,100 degrees Celsius and 1,250 degrees Celsius, 2012 to 2,282 degrees Fahrenheit. Within minutes, the dark gray steel glows bright orange, almost as if it's alive. Imagine standing nearby. You would hear the deep hum of electricity and feel waves of intense heat rolling across the factory floor. A robotic arm quickly transfers the red-hot billet to a forging press before it loses temperature. Timing is everything because even a few seconds of cooling can change how the steel flows inside the die. The glowing billet lands perfectly between precision machine dies, and then the entire factory seems to pause for a heartbeat. What happens next releases enough force to shake the building. With a thunderous crash, the hydraulic press slams shut. Some presses generate 3,000 to 8,000 tons of force, while the largest industrial forging presses exceed 50,000 tons. Under that incredible pressure, the steel doesn't crack. It flows like thick clay, filling every tiny detail inside the forging die. Most people think metal is rigid, but at forging temperatures, it behaves almost like a liquid trapped inside a solid. The secret advantage of forging happens inside the metal itself. As pressure reshapes the steel, its internal grain structure stretches and follows the shape of the tool instead of being randomly arranged. This creates exceptional strength and impact resistance that casting simply can't match. That's why forged wrenches and hammers survive years of punishment, while cheaper tools often crack without warning. Many tools need several forging stages instead of just one. The first die creates a rough outline, the next adds more detail, and the final die forms a finished shape with astonishing precision. Each press cycle lasts only 3 to 10 seconds, allowing modern production lines to forge hundreds of tool blanks every hour. The rhythm becomes hypnotic. Heat, press, sparks, repeat. Freshly forged parts still carry excess metal called flash around their edges. A high-speed trimming press removes this material in less than a second using hardened cutting dies operating under hundreds of tons of pressure. The trimmed steel falls away with a sharp metallic snap, while the finished blank continues down the conveyor. Nothing goes to waste because those scraps return to the steel mill for recycling. The tool may already look complete, but it's still too soft for real work. Now it enters one of the most critical stages, heat treatment. Massive furnaces heat the forged pieces to around 850 degrees Celsius to 900 degrees Celsius, 1,562 to 1,652 degrees Fahrenheit, before they're rapidly cooled in oil, polymer solution, or water. That sudden temperature change locks the steel into an extremely hard, microscopic structure. But here's what nobody tells you. Steel that's too hard becomes dangerously brittle. To restore toughness, every tool goes through tempering, where it's reheated to 180 degrees Celsius to 600 degrees Celsius, 356 to 1,112 degrees Fahrenheit, depending on the tool type. This carefully balanced process sacrifices a little hardness to gain enormous durability. It's the reason a forged hammer can absorb thousands of powerful blows without shattering. After cooling, powerful CNC machining centers take over. Diamond-coated cutting tools spinning at 5,000 to 15,000 revolutions per minute drill holes, machine wrench openings, and create perfectly flat gripping surfaces. Coolant sprays continuously over the cutting area, while robotic loaders feed one part after another with incredible precision. Every movement happens within fractions of a millimeter. Grinding machines polish the working surfaces until every edge meets exact specifications. High-speed abrasive wheels rotate at nearly 3,000 revolutions per minute, throwing showers of tiny orange sparks across protective shields. The air smells faintly of hot steel, while cooling fluid keeps temperatures under control. At this stage, the rough forged blank finally begins to resemble the tool you'll recognize. Some tools now receive protective coatings. Chrome plating creates a mirror-like finish that resists corrosion, while black phosphate coatings reduce glare and improve rust protection. Other premium tools receive advanced powder coatings baked inside industrial ovens for exceptional durability. These finishes don't just improve appearance. They dramatically extend the tool's working life. Finally, logos, size markings, and identification numbers are stamped or laser etched onto every tool. Powerful fiber lasers permanently mark hardened steel in seconds without weakening its surface. Every serial number allows manufacturers to trace that tool back to the exact production batch, furnace, and even the steel chemistry used to create it. The journey seems complete, but the toughest challenge is still waiting. You might think these tools are ready for store shelves, but not yet. Before a single forged hammer or wrench reaches your toolbox, it must survive crushing stress tests, microscopic inspections, robotic vision systems, and the trained eyes of experts who can spot flaws no computer can see. And that's where the next chapter becomes truly fascinating. The factory may look like a place of fire and steel, but hidden behind the noise is a world of astonishing precision. Every forged tool now enters a quality control system where even the smallest flaw can end its journey. Imagine spending hours shaping a perfect wrench, only for an invisible defect smaller than a grain of sand to send it straight to the recycling bin. In modern manufacturing, perfection isn't a goal, it's a minimum requirement. The first inspection begins with AI-powered vision systems. High-speed cameras capture hundreds of ultra-high-resolution images of every tool, while intelligent software compares each one against a perfect digital model. The system detects scratches, cracks, dents, incomplete forging, and surface imperfections in less than a second. What your eyes might miss, artificial intelligence catches instantly. Next comes laser measurement. Precision laser scanners map the entire surface of every tool with incredible accuracy, measuring dimensions within plus or minus 0.02 millimeters, about one-third the thickness of a human hair. If even one jaw opening or striking face falls outside tolerance, the tool is rejected immediately. Most people never realize that such tiny differences can determine whether a tool lasts decades or fails under pressure. But surface perfection isn't enough. Engineers also search for hidden cracks buried deep inside the steel using magnetic particle inspection. The tool becomes magnetized, and a special iron powder flows across its surface. If a microscopic crack exists, the particles gather into a visible line, revealing damage that would otherwise remain invisible until the tool suddenly failed. Premium manufacturers often go even further with ultrasonic testing. High-frequency sound waves travel through steel, bouncing back from hidden voids or internal defects. Powerful computers transform those echoes into detailed images of the metal's interior, almost like giving every tool a medical ultrasound. The process happens in seconds, but it protects users for years. Now comes one of the most dramatic moments inside the factory. Robotic testing machines grip finished wrenches and apply twisting forces that exceed normal working conditions by several times. Hydraulic systems generate tens of thousands of newtons, while sensors record every fraction of movement. If the tool bends too early or fractures unexpectedly, engineers immediately investigate the entire production batch. Impact tools face an even tougher challenge. Automated hammers strike forged chisels and punches thousands of times under controlled conditions to simulate years of heavy use. The repetitive metallic impacts echo through the testing laboratory like distant thunder. Watching the machines work, it's hard to believe these tools will eventually fit inside an ordinary toolbox. Corrosion resistance matters too. Chrome-plated tools spend hours inside salt spray chambers where warm salt mist attacks the surface around the clock. A premium finish can survive hundreds of hours before showing signs of rust, while poor coatings fail much sooner. It's a harsh test, but it's far gentler than disappointing someone who depends on that tool every day. Across an entire production run, rejection rates often stay below 1%, and some world-class manufacturers achieve defect rates measured in only a few parts per million. Every rejected tool returns to the recycling system, where it melts down and begins the journey again. Nothing is wasted because every kilogram of premium steel carries enormous value. Even in factories filled with robots, experienced craftsmen still play a critical role. A skilled inspector can hear a subtle difference when two hammers strike the same surface or feel an almost invisible imperfection with a single touch. Decades of experience allow these experts to notice problems no algorithm has learned to recognize. Sometimes, the most advanced technology in the building is still the human mind. Only after passing every inspection does each tool receive its final approval. Packaging robots place finished products into protective trays before automated systems prepare them for shipment to hardware stores and industrial suppliers around the world. But here's something remarkable. This factory is only one small part of global industry, producing hundreds of millions of forge tools every single year. And the numbers behind that industry are even more incredible than the manufacturing itself. By now, you've seen how a forge tool is born from fire, pressure, and precision, but the scale of this industry is almost impossible to imagine. Every year, manufacturers around the world produce hundreds of millions of forged hand tools, supplying everyone from home DIY enthusiasts to the largest construction, mining, automotive, and aerospace industries. If you lined up just 1 year's production of forged wrenches end to end, they would stretch for thousands of kilometers. The global forged hand tool market is worth tens of billions of US dollars, and demand continues to grow as infrastructure, renewable energy, and advanced manufacturing expand across the world. Millions of skilled workers, engineers, technicians, metallurgists, and machine operators contribute to this industry every day. Behind every finished tool stands an international network of mines, steel mills, shipping companies, factories, and laboratories working together with remarkable precision. Today, China produces the largest share of forged hand tools, followed by India, Germany, the United States, and Japan. Each country brings unique strengths to the industry. Some specialize in high-volume production, while others focus on premium precision tools built for demanding professional applications. Together, these manufacturing powerhouses supply customers in nearly every country on Earth. Think about how far this technology has come. Thousands of years ago, blacksmiths shaped glowing iron by hand using simple anvils and hammers. Every strike depended entirely on human strength and experience. Today, computer-controlled forging presses deliver thousands of tons of force with astonishing consistency, producing tools in seconds that ancient craftsmen would have needed hours to complete. Over the last 50 years, forging technology has changed dramatically. Manual handling has given way to robotic automation, laser-guided measurement, AI-powered inspection, and energy-efficient induction heating. Modern factories produce stronger, more consistent tools while consuming less energy and generating fewer emissions than previous generations. The result is better quality, with a smaller environmental footprint, and the future looks even more extraordinary. Artificial intelligence already predicts machine maintenance before breakdowns occur, while digital twins simulate entire production lines in virtual environments. Researchers continue developing stronger alloys, smarter coatings, and lower carbon steelmaking technologies that could redefine manufacturing over the next decade. The next generation of forged tools may be stronger, lighter, and more sustainable than anything we use today. Did you know that a premium forge wrench can survive torque loads several times greater than the force most people can apply by hand? Did you know that the internal grain flow created during forging is one of the biggest reasons these tools outperform cast alternatives? And here's one more surprise. Many professional mechanics keep forged tools for decades, sometimes passing them down through generations because they simply refuse to fail. From iron ore buried deep beneath the Earth's surface to a glowing river of molten steel, from enormous forging presses delivering incredible force to microscopic inspections measuring fractions of a millimeter. Every stage exists for one reason: to build a tool you can trust when it matters most. Most people see only the finished product, but now you've witnessed the hidden world of engineering, science, craftsmanship, and technology that makes it possible. The next time you pick up a forged tool, you'll know you're holding far more than steel. You're holding generations of innovation shaped by fire. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.